In this video, we're going to practice curve sketching. We've actually done a lot of curve sketching already when we studied concavity. We sketched a lot of the graphs to visualize what it was we were doing. In this lesson, you're just focusing primarily on curve sketching. So I'm going to go through a couple of examples with you, but there are other videos out there. All the videos related to the first derivative test and second derivative test featured some curve sketching. Those with the second derivative test also showed where the graph was concave upward and concave downward. So you've got more examples there. But in this video, we'll do an example involving an exponential function. Either later in this video or in another video, we'll do one involving inverse trig functions and logarithms, just so that you have some more advanced or interesting examples involving transcendental functions. Okay, so let's say we want to sketch this graph. We don't have a graphing calculator, we don't have access to a computer, and we want to know what's going on. Even when we do have a graphing calculator or access to a computer algebra system that will graph for us, we need to know enough about the graph to infer where to look. A graphing calculator is only going to show you part of a graph on a window. So you'll sketch the graph, you'll type it in, and the graphing calculator might zoom in right here. And maybe on that window the graph looks like this. But there might be all kinds of interesting things going on over here, and you would never know it because your window is only showing you that part. In order to set your window, in order to have a very good sense of where all of the interesting things happen. So points of inflection. Where does the graph go from concave upward to concave downward? Extrema. Where do we have relative mins and relative maxes? Are there any flat points where the derivative is 0 and the function goes from increasing to increasing or decreasing to decreasing? All of those are important. Also, we might be interested in asymptotes, intercepts. All of this can help us to get a very good sense of what's going on, so that we're not blindsided by our calculator. Our calculator is only going to show us a little picture like this. We have to know enough about the mathematics and about the function itself in order to set that window. So that's what this is about. This will allow us to graph the function in such a way that all the interesting features, as far as the first derivative and second derivative are concerned, are shown in our graph. So that's why we do this. So let's say we've got a function like this, and I want to sketch the graph. The first thing I always do, is I try to find the domain of the function. So find the domain. And I'll write this down, even though you've heard me say it many times. You want to exclude x values that cause division by 0, even roots of negative numbers, and logarithms of negative numbers or 0. And if we don't have any of those problems, then the domain is all real numbers. If we're given a function that's defined by a single equation, and the pieces that the function is built from are those standard functions that we've talked about, so polynomials, exponentials, logarithmic functions, trig functions, inverse trig functions. If we're adding, subtracting, multiplying, and dividing those to get our function, the implied domain is all the x values that don't cause these problems. So notice we don't have any division, so there's no danger of dividing by 0. There are no even roots, excuse me, so we're not going to take the even root of a negative number and accidentally get a complex number. There are no logarithms, so there's no concern about taking the log of a negative number or 0. So the domain of this function is all real numbers, which we can write that way or we can write that way. Now the next thing we like to do is find the intercepts of the function, because we're curve sketching. We want to know, where does this graph cross the x-axis and the y-axis? To find the x-intercept, remember how this works. If you've got a function and you're trying to figure out where the function crosses the y-axis and where the function crosses the x-axis, maybe it looks like this, maybe not. We're trying to find that y-intercept and that x-intercept, and usually we're talking about the ordered pairs, not just the x or y value. Well, we use the geometry of the situation to figure out what that y value is. The y-intercept lies on the y-axis, and I know this is counterintuitive, but on the y-axis, x equals 0. And I think it makes sense if you actually remember your vertical lines are x equals 0, x equals 1, x equals 2, x equals 3, x equals -1, x equals -2, x equals -3. All those are vertical lines, so the y-axis is a vertical line and it's x equals 0. It's that x value in the middle between all the negative numbers on this side and all the positive numbers on that side. So to find the y-intercept, we set x equal to 0 and solve for y. When using function notation, all that means is you're replacing x with 0 in the original function, and then you're simplifying. 3 minus 0 is 3. 3 to the 0 is 1, so we get y equals 3. So the y-intercept is an ordered pair. It's x equals 0, y equals 3. So our graph would cross at 3. If that was what our graph looked like, it would cross there at 3. Similarly, if I want to find the x-intercept, well, all the negative y values are down here and the positive y values are up here. On the x-axis, y is equal to 0. So if I want to figure out where my graph crosses the x-axis, I set y equal to 0 and solve for x. So I'm replacing f of x with 0 because f of x and y are the same thing, right? So we're setting that y value equal to 0 and we're solving for x. Now this is a product. This times this equals 0 if this factor equals 0 or this factor equals 0. So either 3 minus x equals 0 or 3 to the x equals 0. But remember, 3 to the x looks like this. That's never 0. It doesn't matter what x is. Our graph gets very, very close to 0. The y values get very close to that y-axis, or excuse me, the x-axis where y is equal to 0, but they never actually get there. If x is -1 million, we get 3 to the -1 millionth power. So it's 1 over 3 to the 1 millionth. It's a very, very tiny positive number. It's not 0. So this never happens. We don't have to worry about that. This does happen. So we'll solve for x by adding x to both sides, and we get x equals 3. All right. So I actually have no idea what the graph looks like in between. Right now, I just got two intercepts. X equals, when x is 0, y is 3, and when y is 0, x happens to be 3. Okay. So I've got my domain, I've got an x-intercept and a y-intercept. And we would also sketch any asymptotes if we had any, but our domain was all real numbers, so there are no asymptotes. The next thing we might want to do is figure out where our function is increasing or decreasing. To do that, we're going to take the first derivative, set it equal to 0 to determine the intervals where f prime changes from positive to negative or negative to positive. Basically, we're figuring out where the slope is 0. And then we'll determine the sign of f prime on each of those intervals. That tells us whether the function's increasing or decreasing. So we will compute f prime. And then once we have f prime, we'll find the critical values. F prime of x is the derivative with respect to x of 3 minus x times 3 to the x. Since I've got a product here, I'm going to use the product rule. The derivative of a product is the derivative of the first function times the second function, undifferentiated, plus the derivative of the second function times the first, undifferentiated. Okay, then we just compute those two derivatives. Derivative of 3 is 0. Derivative of negative 1 times x is negative 1. And over here, I've got 3 to the x power. There's a rule for that. If you've got a constant raised to the x, it's just an exponential function to base other than e. You get exactly the same exponential times the natural log of the base. So the slope of a function raised to the x is very similar to the original function. It's just multiplied by this constant, the natural log of the base. So in our case, the base is 3, so we get 3 to the x times natural log of 3. And remember, 3 is a constant, so natural log of 3 is a constant. So this is our derivative. We have a negative 1 times 3 to the x plus 3 to the x times natural log of 3 times the quantity 3 minus x. And I see that I have two terms. And remember, we want to find critical points in just a bit. So it's helpful if we factor this. If we can factor this, we should factor this because it'll make it easier to find the critical points. So we look at this as a single term and this as a single term, and we ask ourselves, what do these guys have in common? Well, they have a 3 to the x in common. So I can factor that out. And then I ask myself, 3 to the x times what gives me a negative 3 to the x? Gives me that first term. Well, it's just a negative 1. And then I ask myself, 3 to the x times what gives me this? Well, I already have the 3 to the x, but I need the natural log of 3, which is a constant, times that quantity 3 minus x. Now you can distribute that natural log of 3 if you want to, but you don't have to. So f prime is equal to 3 to the x times negative 1 plus, if I'll distribute, 3 natural log of 3 minus natural log of 3, which is just a constant, times x. Okay, so we've computed f prime and we've factored it. It's always a good idea because we're about to set it equal to 0. Okay. So now we will find the critical points of the function. By setting f prime equal to 0 and solving for x. So f prime was this. We had 3 to the x times negative 1 plus 3 natural log of 3 minus natural log of 3 times x. And we're setting this equal to 0 and solving for x. Well, we've got this times this equals 0. But an exponential function is never 0. So if I have something that's never 0 times something equals 0, well then the other something, that has to be 0. So from this we get this factor, 3 natural log of 3 minus 1 minus natural log of 3 times x. that must be 0. And I'm solving for x. Now this looks much more complicated than it is. Natural log of 3 is just a number. -1 is of course just a number, and this is just a number times x. So this is a simple linear equation in x, even though it looks complicated. You just have to remember, if there's a number inside a log, it's just a constant. You would treat this natural log of 3 the same way you would treat a 5 as you're doing the algebraic manipulation to get x by itself. So if I want to get x by itself, the first thing I need to do is I need to get this by itself on one side. Since I'm subtracting natural log of 3 times x over here, to undo that, we will add natural log of 3 times x to both sides. And we're trying to get x by itself, and it's multiplied by something. We undo multiplication with division, so we'll divide both sides by natural log of 3. And that is our critical point. X equals 3 natural log of 3 minus 1, all divided by natural log of 3. You can divide these terms individually by natural log of 3, so we could do 3 natural log of 3 divided by natural log of 3 minus 1 over natural log of 3. You could write it this way. Either way is fine. I think I prefer this single fraction as opposed to the 3 minus that other fraction. But either way is fine. Now to create my sign chart and think of test values, it's helpful to get a numerical approximation of this. So I'll just do actually that one, 3 minus 1 over natural log of 3. My calculator knows order of operations with addition, subtraction, and division, so I'm good there. I don't need any parentheses. Often we do. When in doubt, just use extra parentheses. So we've got about 2.09 as our critical value. We also have to ask ourselves, are there any x values for which this is undefined? And there aren't. There's no danger of dividing by 0. There are no even roots of negative numbers. And there are logarithms, but there's no logarithm of a function of x. So there's no danger of taking the logarithm of a negative number or 0. So this is well defined for all real numbers x. So it turns out we have a single critical point, x equals 3 minus 1 over natural log of 3. So we're going to use that single critical point to create our sign chart now for f prime. And then using our sign chart, we'll figure out where this function is increasing or decreasing. I'm just drawing a number line. I put my critical point on the number line. Actually, I think I am going to use that simplified version after all. 3 minus natural log of 3, which is about 2.09. And I'm interested in the sign of this. F prime is the product of two factors. It's the product of 3 to the x and this other factor, 3 natural log of 3 minus 1 minus the quantity natural log of 3 times x. 3 to the x is always positive. It doesn't matter what x is. Now this one, I'm not sure, so I might substitute in x equals 0. That's to the left of 2.09, and so I get 3 natural log of 3 minus 1. Pretty sure that's positive, but let's check. Yep, it's positive. So f prime is a positive times a positive, which makes it positive on the interval from negative infinity to our critical point. And then over here, let's plug in x equals 3. Well, actually, if x equals 3, I've got 3 natural log of 3 minus 3 natural log of 3 minus 1. So I'll just get a negative 1. So I have a positive times a negative, which is a negative. So I've created a sign chart for f. That's enough to help me determine where the function is increasing and decreasing. So let's state the intervals where f is increasing I'm going to say or decreasing. So the function is increasing where f prime is positive. So when the first derivative is positive, the graph is going up. So that is on the interval from negative infinity to 3 minus natural log of 3. Or 1 over natural log of 3, sorry. It's always an interval that goes from here to here. We read it from left to right, and if you're on the far end, it's going to be a negative infinity or a positive infinity. On the other side, the first derivative is negative. If the first derivative is negative, that means the slopes are all negative. If the slopes are all negative, that means the function is decreasing. So the function's decreasing from this x value to infinity. Okay. Now, we can also use the first derivative test at this point to find extrema. This critical value corresponds to, I think we can all see it, it's a relative max, because the slope goes from positive to 0 to negative. Because this was a critical value that was associated with a 0 slope, remember? So that means we're at the top. Slopes are positive on this side, so the function's increasing. Then slope is 0. Then the slope is negative. So that has to be a relative max. So we can use the first derivative test to find relative extrema. Remember what the first derivative test says. If your function changes from increasing to decreasing or decreasing to increasing, you have either a relative min or a relative max. So if f prime changes signs, you are that x value, that critical value, corresponds to a relative max or a relative min. Now, the relative maximum value is not the x value, and it's not an ordered pair. Even if WebAssign says it's an ordered pair, that's technically wrong. The relative maximum is actually the y value at this x value. So we know that we have a relative maximum at this x value. But the relative maximum value is the function evaluated at the critical point. It's the y value there, not the x value. If somebody asked you, if somebody gave you a height function, they said, this is the height of a ball as a function of time. And I asked you, what's the maximum height? You wouldn't tell me the time and the maximum height. You definitely wouldn't tell me the time. You'd tell me the height. So the maximum value of the function is actually the y value. So I want to substitute this for my x in the original function, and the original function was 3 minus x times 3 raised to the x power. So I have 3 minus the quantity 3 minus 1 over natural log of 3 times 3 raised to this power. That looks really horrible, but that's okay. Distribute the negative sign. Then we'll have 3 minus 3, a negative times a negative is a positive. You don't really need that multiplication that I'm suggesting with that dot. I just put it there for emphasis, but it's not necessary. So I have 1 over natural log of 3 times this. So the relative maximum value is actually 3 raised to this power, all divided by natural log of 3. And let's find that y value, or at least that is the y value, but let's find a numerical approximation for it. So I have 3 raised to this power, and the power is 3 minus 1 divided by natural log of 3. That's my numerator, and we're dividing all of that by natural log of 3. That's the denominator. So we get about 9.04 when the x value is this. So the point on the graph is about 2.09 and 9.04. But the exact value is this x value with this y value. That would be the ordered pair I would type in if WebAssign wanted an ordered pair. But remember, the relative max is not the ordered pair. The relative max is the y value. So we want a maximum value of the function, so you should have a function value whenever you're asked for a min or a max. Okay, so we were asked to state the intervals where the function was increasing and decreasing, and we found them. Now we want to find the intervals where the graph is concave upward or concave downward. And we did extrema using the first derivative test. We can also confirm our result using the second derivative test. Okay, so now we want concavity. So we're basically going to do the same thing with the second derivative that we did with the first derivative, but we don't call it finding critical points anymore. We just call it setting the second derivative equal to 0 and solving for x. Those are possible points of inflection. So we'll compute the second derivative, and then we'll set it equal to 0 and solve for x to create a sign chart for f double prime. So f double prime is the derivative with respect to x of 3 to the x times this quantity, 3 natural log of 3 minus 1 minus the quantity natural log of 3 times x, close parentheses, close your brackets. Now this looks a mess, but that's just a constant. That's no big deal, and that's just a constant times x. So when I take the derivative of this, I'm just going to use the product rule. Here's my first function, and there's my second function. According to the product rule, we get derivative of the first times the second function, undifferentiated, plus derivative of the second function times the first, undifferentiated. Derivative of a to the x is a to the x, so exactly the same exponential, times natural log of the base. So you have natural log of 3 there. And then over here, that is a constant. The derivative of a constant with respect to x is 0. That's also a constant, so the derivative of that is 0. This is a constant times x. The derivative of a constant times x is the constant that's multiplying x. So this whole thing is negative natural log of 3. So we end up with this. We've got 3 to the x times natural log of 3 times 3 natural log of 3 minus 1 minus natural log of 3 times x, close parentheses, minus natural log of 3 times 3 to the x. Wow. Got a lot going on there. Okay. Now we computed f double prime so we could figure out where the graph was concave upward and concave downward. So we need to factor this. So we're computing f double prime and factoring it if possible. And this time it is possible. And the way you want to do it is you want to think of this group and this group as separate terms. And you say to yourself, okay, what do these two groups have in common? Well, I see they both have a natural log of 3, and they both have a 3 to the x. So I can factor that out from everything. And then I ask myself, 3 to the x times natural log of 3 times what gives me the first term? Well, that was already factored out from there, so it's obviously everything else. And then I say to myself, 3 to the x times natural log of 3 times what gives me this? And it's just the negative 1 that's missing. So I have 3 natural log of 3. Negative 1 minus 1 is minus 2. Okay. So that's f double prime. To create our sign chart for f double prime, we're going to set f double prime equal to 0 and solve for x. So I've got this times this equals 0. The only way a product is 0 is if one of the factors is 0. So the only way this could be 0 is if 3 to the x were 0. But exponentials are never 0, so we don't have to worry about that. 3 to the x looks like this. It gets close to 0, but it never gets there. All right. Natural log of 3 is a constant. Of course, it's never 0. And then the last possibility is that this factor, it's linear in x. It looks really messy, but this is just a constant plus a constant times x. That linear expression in x is equal to 0. That's the third possibility. Turns out it's the only possibility that leads to an x value. So I'm trying to solve this linear equation for x. So I get the x term by itself first. I'm subtracting natural log of 3 times x here. To undo that, I add natural log of 3 times x to both sides. So I have 3 natural log of 3 minus 2 equals natural log of 3 times x. And this is multiplication. Something times x is something else. In order to undo multiplication, we divide. So x equals 3 natural log of 3 minus 2. And you can divide both terms by natural log of 3 if you want to. So we get 3 minus 2 over natural log of 3. Very similar to our critical point from earlier. Earlier we had 3 minus 1 over natural log of 3. Now we have 3 minus 2 over natural log of 3. Now we should also consider when the second derivative is when the second derivative is undefined. But exponentials are always well defined, and this is linear in x, that's always well defined. So this is our one possible point of inflection for our function. It's not a critical point, it's kind of like a critical point. It's just we use the second derivative instead of the first derivative. That is the number that's going to go on our sign chart for f double prime. And it helps to know what this is numerically, just have a numerical approximation. That's the exact value. The numerical approximation is 1.18. Okay, so now we've got f double prime, and we want a sign chart for f double prime. And I've got my critical value 3 minus 2 over natural log of 3 over here, and that's about 1.18. Now f prime is the product of these factors. It's natural log of 3, which is positive, times 3 to the x. I'll think of that as one factor. 3 to the x is always positive, regardless of what x is. And then I've got the second factor, 3 natural log of 3 minus 2 minus natural log of 3 times x. I want to pick test values to the left and right of x equals 1.18. X equals 0 is the easiest test value over here. So when x is 0, this is gone. So I just have 3 natural log of 3 minus 2. Pretty sure that's positive. Let's check it out. So we get 1.2958, or about 1.3. So it's positive. And over here you can pick any test value you want. I'm going to choose x equals 3 again, because then I have 3 natural log of 3 minus 3 natural log of 3, and those cancel. So I'll just have the negative 2 that's left. So f double prime is a positive times a positive on this interval, so it's positive. And f double prime is a positive times a negative on this interval, so it's negative. So now we've got a sign chart, and we can use this to interpret, or we can use this to infer the concavity of the original graph. So let's state the open intervals. where the original function f, or I should say the graph of the original function f, is concave upward or concave downward. Well, it's concave upward when the second derivative is positive, so the graph is going to look like that over here. It's concave downward where the second derivative is negative, and this x equals approximately 1.18, that's our transition point. The xy pair, this x value and the y that goes with it, that is the point of inflection on the original graph. So let's do this concavity part first. The graph is concave upward on this interval. Remember, on the far left, we're going from negative infinity to that point. So the graph is concave upward here, and that's approximately the interval from negative infinity to, positive 1.18. And the graph is concave downward on this other interval, from the critical point to infinity. I keep calling it a critical point. I'm misspeaking. It's just an x value where the second derivative happens to be 0, but calculating it was a lot like calculating a critical point. Okay. So we know where the graph is concave upward and concave downward now, and the xy pair, this x value and the y value that goes with it, that is our point of inflection. Okay, so we need to find the y value that goes with this x value. So when x is equal to 3 minus 2 over natural log of 3, the y value on our graph is given by this. The original function was 3 minus x times 3 to the x. So we're subtracting x, and x has two terms, so you need parentheses there. So this is 3 minus 2 natural log, or over natural log of 3, and in our exponent we have 3 minus 2 over natural log of 3. And if you distribute this negative and simplify, excuse me, the 3's reduce, and you end up with 2 times 3 raised to the 3 minus 2 over natural log of 3, all divided by natural log of 3. Let's find out what that is approximately. So we have 3 raised to the 3 minus 2 divided by natural log of 3. That's right here. Multiply by 2 to get the numerator. Divide by natural log of 3 to approximate the y value. And the y value is approximately 6.65. So the point of inflection is this. xy equals 3 minus 2 over natural log of 3, and 2 times 3 raised to this power, which is approximately 1.18 and 6.65. Approximately there on the graph. Okay, I think we have enough information to graph this function. We know where the graph is concave upward, concave downward. We know where it's increasing and decreasing. We know the intercepts. We know the domain. There were no asymptotes. So let's put all of those pieces together to graph the function now. So here's my summary. The domain was all real numbers. The y-intercept, which came from setting x equal to 0 and solving for y, is 0, 3. The x-intercept, which came from setting y equals to 0 and solving for x, was 0, 3. We had a relative maximum. And the relative maximum was f of 3 minus 1 over natural log of 3, which is this value. Now again, WebAssign might want you to write it in ordered pairs, but the true relative maximum is actually the y value. And that's approximately a 9.04. So the point on the graph that's corresponding to this relative max, so the x at the max, the relative max, and then the y value that happens to be a relative max is approximately equal to this. X was approximately 2.09 and y was approximately 9.04. The exact values of those were this x value with that y value. We found a point of inflection. And the point of inflection was 3 minus 2 over natural log of 3, and then the y value was this. So when we look at our intervals where the graph is increasing and decreasing, concave up and concave downward, it helps to include both the x value for the point of inflection and the x value for that relative max. So the x value for the point of inflection was 3 minus 2 over natural log of 3, which is approximately the 1.18. And then the x value for the relative max was 3 minus 1 over natural log of 3, which is approximately 2.09. So let's look at the function's intervals where it's increasing and decreasing. We were told that the function is increasing on the interval from negative infinity to 3 minus 1 over natural log of 3. I just misspoke. We weren't told that. We calculated that. We found that the first derivative was positive on that interval. And the function is decreasing on the other interval, the rest of the number line. So our function is increasing here and here, and it's decreasing here. Now the graph is concave upward, on this interval. Whoops, 3 minus 2 over natural log of 3. And concave downward on this other interval, 3 minus 2 over natural log of 3 to infinity. So it's concave upward here, and then here it's concave downward for both of these intervals. Okay, so this is enough to help us graph the function. What do we know? Well, we know the domain is all real numbers. When x equals 0, y equals 3, and vice versa. And the point x equals 2.09, y equals 9.04 corresponds to the location of a relative maximum. and at x equals approximately 1.18 and y equals approximately 6.65, we've got a point of inflection. And we know the graph crosses the y-axis there and the x-axis here. And our function was 3 minus x times 3 to the x. So I can actually infer end behavior as well. The limit as x goes to positive infinity of this. 3 to the x will be approaching infinity, and then this will be approaching negative infinity. So I've got a large negative number times a large positive number, so we should go to negative infinity as x goes to negative infinity. Or excuse me, as x goes to positive infinity, and as x goes to negative infinity, this is approaching infinity and this is approaching 0. That is an infinity times 0 indeterminate form, which we'll discuss later using something called L'Hopital's rule. We haven't gotten there yet. I'm just going to tell you, due to L'Hopital's rule, this turns out to be 0. You're like, what? I know. But this exponential goes to 0 faster than that goes to infinity. So the exponential dominates and we get 0. Okay, we'll talk about that later when we get to L'Hopital's rule. So with this behavior in mind, okay, what does that tell us? Let's fill in the rest of our graph. On the interval from negative infinity to 3 minus 2 natural log, or 2 over natural log of 3. So the interval from negative infinity to our critical point, or excuse me, our point of inflection right here. The graph is concave upward and it's increasing. And then from here to here, we've got a graph that's concave downward and increasing on one side and decreasing on the other. And if you're saying to yourself, how is that even possible? Here's what our concave upward graph looks like generally, and that's our general concave downward graph. If the function's increasing and concave upward, it's going to look like that side of that parabola. It's going up and it's concave upward. Now here, where it's concave downward and it goes from increasing to decreasing, that's exactly what we're going to see. We're going to see that parabolic shape. It's concave downward and increasing on that side, and concave downward and decreasing on the other side. So this is our point of inflection. That's just some calculations we did to infer end behavior. We weren't asked for that, but I just did that because I really wanted to see what the whole graph looked like, and I think this is what it looks like. And we've got a relative max right here. And the relative maximum value is 3 raised to the 3 minus 1 over natural log of 3 divided by natural log of 3. And it occurs at this x value that goes with it. X equals 3 minus 1 over natural log of 3. And we've got our two x and y intercept. Our y-intercept is right there, our x-intercept is right there. So we don't need a graphing calculator, we could just do this. You know all about this function because we know derivatives, and we know how to find domain, and we understand intercepts. We can see this, we see this function, and we can infer exactly what it looks like, or not exactly what it looks like. We can infer a lot about what it looks like though. using the first derivative to determine where it's increasing and decreasing, using the second derivative to determine where the graph is concave upward and concave downward, and then looking at asymptotes, intercepts, the domain, points of inflection, end behavior, all of that. We put all of those pieces together, and we're able to sketch this graph. Now I'm not 100% sure about all the details, but I know it's concave upward until we get to here, and I know it's concave downward until we get to, until on this interval from here to here, and I know it's increasing until we get to here, and then it's decreasing here, and I know it crosses there, and I know the end behavior is this and this. And that's pretty good. It's pretty decent graph, given that we didn't have technology graphing it for us.